and welcome to this video looking at enthalpies. In this video we will be concentrating on the calculations related to the enthalpy of combustion, enthalpy of solution and enthalpy of neutralisation. For the higher course you're only expected to know the enthalpy of combustion, however the calculations for enthalpy of solution and enthalpy of neutralisation are very similar, and it would probably be useful that you have some sort of knowledge of these calculations if you're going to take chemistry on further. So the first calculation that we're looking at is the enthalpy of combustion. The definition for the enthalpy of combustion is the energy that is released when 1 mole of any substance is burned completely in oxygen. The substances that we tend to focus on are the carbon-based substances, an example being methane. The complete combustion of methane would be CH4 plus 2O2 to give carbon dioxide and 2 water. So all of the carbon is converted into carbon dioxide and all of the hydrogen is converted into water. If it is required to put a half into the equation to balance, then that's fine, and it would go in here probably in front of the oxygen. Looking at the calculations to do with enthalpy of combustion, this takes on your E equals cm delta T calculation from National 5 and just takes it a little further. You'll notice that when writing the equation I've put a minus in front here. That's because we're having energy released, so we have the negative value for an exothermic reaction. So in the paragraph it tells us we have 4.6 grams of ethanol, and this raises the temperature of 500 centimetres cubed of water by 57 degrees. And we are to calculate the enthalpy of combustion for ethanol. So the first thing we're going to do is have a look at calculating E equals cm delta T. So C is in your data book and is 4.18 kilojoules per kilogram per degree Celsius. The M is always the mass of water, so we have 500 centimetres cubed, so we're going to divide that by 1000 to get into kilograms, so we have 0.5 kilograms, and then finally our delta T is 57. Okay, so we're going to put these numbers into our equation. So we have E equals negative 4.18 times 0.5 times 57. And if we do that, we get a value of negative 119.13 kilojoules. Now that's not kilojoules per mole because we haven't burned a whole mole of ethanol, we've only burned 4.6 grams. So the second part we have to look at is how many moles of ethanol did we burn. So moles equals mass divided by gram formula mass. You have 4.6 grams divided by a gram formula mass of 46 to give you 0.1 moles of ethanol burned. To work out the enthalpy of combustion, which is in kilojoules per mole, we're going to do delta H equals energy divided by moles burned. So we have negative 119.13 divided by 0.1 moles gives an enthalpy of combustion of 1191.3 kilojoules per mole. And you can work this out using the units as well. So we have kg per mole, so we have kg divided by moles. There is a second way to calculate this, where we have 4.6 grams of ethanol, we have 500 centimetres cubed of water, and we're raising the temperature by 57 degrees. The first part of the calculation is exactly the same, where you have the E equals negative cm delta T, and that gives you the same value of 119.13 kilojoules. The second part uses proportion. So if 4.6 grams of ethanol gave you 119.13, we're trying to scale it up to 1 mole. So one thing that we can do is to divide both sides by 4.6. And that would give us 1 gram. And then we can scale up by timesing by 46. which is the gram formula mass. And on doing that, you would end up with exactly the same answer. It's entirely up to you which version you decide to use. So why don't you try and pause the video now? The example that you're going to look at is 0.22 grams of propane burning to heat 0.25 kilograms of water from 21 degrees to 31 degrees, and you're trying to calculate the enthalpy of combustion for propane. Using the first method that we've looked at, we have 0.22 grams of propane. We're heating 0.25 kilograms of water, and it's going from 21 degrees to 31 degrees. So we're going to use E equals negative Cm delta T, where we have C equals 4.18. We have M given to you in the question already in kilograms, so watch out for that, 0.25. And then delta T is 31, so the end temperature minus the start temperature to give us 10 degree rise. I'm going to put those numbers into the equation. So we get 4.18 times 0.25 times 10, which gives you an energy of minus 10.53 kilojoules. Then looking at how many moles of propane that we burned, so propane's formula is C3H8. So moles equals mass divided by gram formula mass. So we've burned 0.22 grams, and gram formula mass of 44 means that we have used 5 times 10 to the minus 3 moles. Then as before, we're doing delta H equals energy divided by moles burned. So 10.53 divided by 5 times 10 to the minus 3 gives you an enthalpy of combustion for propane of minus 2090 kilojoules per mole. If we look at using the other method, the E equals negative Cm delta T is the same, so minus 10.53 kilojoules. So if 0.22 grams of propane gave you minus 10.53, we can divide by 0.22 to get 1 gram. And then multiply by the gram formula mass of propane, which is 44, to scale back up again. So minus 10.53 divided by 0.22, then all multiplied by 44 to give you minus 2090 kilojoules per mole. The second type of enthalpy that we're looking at today is the enthalpy of solution. Enthalpy of solution is the energy change associated with dissolving 1 mole of an ionic substance in water. So for example, if we had solid sodium chloride and we're dissolving it in water, we will end up with aqueous sodium ions and aqueous chloride ions. And there would be an energy change associated with this. The calculation that you carry out is very similar to the enthalpy of combustion calculation. So here we have 5.3 grams of sodium carbonate, and we're dissolving this in 100 centimetres cubed of water, and when this happens we have a temperature rise from 20.5 to 23.5. So the first thing we need to do is to calculate E equals minus Cm delta T, just as we did for enthalpy of combustion. So again, just using the information about water for this, we have C equals 4.18, M is the mass of the water that we were using, so 0.1 kilograms, and then delta T is the end temperature, 23.5, minus the start temperature, 20.5, to give us a temperature rise of 3.5 degrees. So if you put that into the equation, then we get an energy change of minus 1.254 kilojoules. And that is just for 5.3 grams of sodium carbonate. So we need to look at if we were to dissolve a whole mole of sodium carbonate, what would the energy change be? So for sodium carbonate, you have a formula of Na2CO3. And just like before, you're going to work out the moles as mass divided by gram formula mass. So we have 5.3 grams. We have a gram formula mass of 106. So we dissolved 0.05 moles. Delta H for your solution is just energy divided by the moles dissolved. So we have minus 1.254 divided by 0.05 to give you an enthalpy of solution of negative 25.08 kilojoules per mole. So when you dissolve sodium carbonate into water, it is an exothermic process, so heat will be released. Like the enthalpy of combustion, you're also able to do the final part using proportion. So here we would have the E equals negative Cm delta T from before, which was minus 1.254 kilojoules. So if you have 5.3 grams of sodium carbonate, this gives out 1.254 kilojoules of energy. If you have 1 gram, you divide both sides by 5.3 and then multiply up by the gram formula mass, which is 106. To get you to the same answer. Here's a second example looking at the enthalpy of solution for ammonium nitrate. So just like before, we're going to look at what we have in the question. So we have 8 grams of ammonium nitrate. We're dissolving that in 200 centimetres cubed of water. And this time it's causing a temperature fall of 3 degrees. So we're using the equation E equals minus Cm delta T. And we're going to continue with the minus here. We have C equals 4.18. M is the mass of water, so it's 0.2 kilograms. And then delta T in this case, because it's a temperature fall, is minus 3. We're going to put these values into the equation. So we have minus 4.18 times 0.2 times negative 3. And as you can see, this will cancel out and give us a positive energy of 2.508 kilojoules. And that's for 8 grams of ammonium nitrate. Ammonium nitrate has the formula NH4NO3. And we're trying to calculate the moles that we use. So that's moles equals mass divided by gram formula mass. So it's 8 divided by 80 to give us moles of 0.1. And then like before, we have delta H equals E divided by moles. So that's going to be 2.508 divided by 0.1 to give us 25.08 kilojoules per mole. So this is an endothermic energy change. When ammonium nitrate is dissolved in water, you have a temperature fall, so you would expect to have a positive value here. We can do the proportion method as well, so using E equals 2.508 kilojoules, if 8 grams of ammonium nitrate gives you 2.508 kilojoules, you can divide by 8 to get to 1 gram. And then multiply back up by the gram formula mass, which is 80, to get to a mole, which will give you the same answer as before, 25.08 kilojoules per mole. This example, we're looking at 4 grams of sodium hydroxide dissolving in 0.25 kilograms of water, and we have a temperature rise of 4 degrees, and we're to calculate the enthalpy of solution. So the first step is always to calculate E equals minus Cm delta T. So C equals 4.18. M is the mass of the water, 0.25 kilograms, and delta T is the temperature rise in this case, which is 4 degrees. So if we put these into the equation, we have negative 4.18 times 0.25 times 4, and that gives us a value of negative 4.18 kilojoules. And that is for 4 grams of sodium hydroxide. We need to find for a mole of sodium hydroxide. So first of all, we need to calculate how many moles of sodium hydroxide we used. So we have moles equals mass divided by gram formula mass. So the mass is 4, gram formula mass of 40, giving you 0.1 moles used in this experiment. Delta H is the energy divided by the moles. So that's negative 4.18 divided by 0.1 to give you negative 41.8 kilojoules per mole. Using the proportion method, you use the same energy that was calculated before, so E equals Cm delta T of negative 4.18, and here we have 4 grams giving us negative 4.18 kilojoules. 1 gram, we would need to divide this all by 4, and then multiplying up to the gram formula mass, which is 40, we'd have negative 4.18 divided by 4, all multiplied by 40, to give you negative 41.8 kilojoules per mole. The final type of enthalpy that we're looking at is the enthalpy of neutralisation. So this is the energy change associated with the production of 1 mole of water during a neutralisation reaction between an acid and a base. So for example, if we had half a mole of sulfuric acid reacting with 1 mole of sodium hydroxide to produce half a mole of sodium sulfate and 1 mole of water, we would be looking at the energy change associated with this reaction. So the first thing we need to do for these ones is to write out a balanced equation. So here we have sodium hydroxide reacting with hydrochloric acid to give you sodium chloride and water, and that equation is already balanced. So your sodium hydroxide, we have 100 centimeters cubed and we have 1 mole per litre, and for hydrochloric acid you have the same value, so we have 100 centimeters cubed and 1 mole per litre. The first calculation that we're going to do is the E equals Cm delta T calculation. In this case we're still using C as 4.18 as we're doing this in water. M is going to be the total of these two values here. So our mass of water will be 0.2, and then our temperature change here is 7 degrees. So if we put all of that into the equation, we get an energy value of negative 5.852 kilojoules. The next thing we need to do is to work out how many moles of water we actually produced. So if we take one of our reactants, for example sodium hydroxide, and we look at the moles of sodium hydroxide that we used, moles equals concentration times volume, so we have 1 times 0.1 to give us 0.1 moles of sodium hydroxide. Moles of sodium hydroxide are equal to the moles of water produced, looking at the mole ratio within the equation, which means that you produced 0.1 moles of water. So just like we have before, delta H equals E divided by the moles. So we have negative 5.852 divided by 0.1 to give us negative 58.52 kilojoules per mole of water produced. Here's an example for you to try. Pause the video now. In this example, we have nitric acid, HNO3, and potassium hydroxide, KOH, producing potassium nitrate and water. And this equation is balanced as it's written there. So we have 100 centimetres cubed of 0.5 molar nitric acid, and we have the same values for our potassium hydroxide. And we have a temperature rise of 3.5 degrees. So if we do E equals negative Cm delta T, we have negative 4.18 multiplied by the total volume, and putting that into a mass is 0.2, and then the temperature rise of 3.5 to give you an energy change of minus 2.926 kilojoules. Now we need to calculate the number of moles of water that were produced, so we're going to base that on the moles of HNO3, which is going to be concentration times volume. So we have 0.5 times 0.1, which gives you 0.05, and this is equal to the moles of water. So if we now do delta H equals E divided by moles, we'll have negative 2.926 divided by 0.05 to give you an enthalpy of neutralisation for this reaction of minus 58.52 kilojoules per mole. Thank you for watching this video on enthalpies. I hope that you found it useful. Remember to subscribe or follow me on Twitter at Miss Adams Chem for regular updates on new videos.